So we need to go through the different kind of models here, kind of finish off some of our talk of models by relating it here to what we've been talking about with light. And if you remember, we had light as acting both as a particle and a wave, and so we also use that to, and at the same time, we kind of had this field of spectroscopy that was developing. So Niels Bohr, who was a Danish scientist, was actually the person who was able to link these ideas together, specifically the idea of light as a particle as well as the spectrum together. So he was able to actually explain the bright line spectrum of hydrogen. And and to do this, he actually created a new model of the atom that we call the Bohr model or the planetary model. What he did was he added electricity to hydrogen gas at a low pressure in a tube, and it was kind of like a neon light. So what it did was it gave off visible light that was observed through a prism. And so what he saw was this. So we have these four very distinct lines. Okay. So he said that this line pattern is due to the quantized electron energy. So just like what Planck was saying, he was able to, kind of relate those ideas. So as the atom, or as the electron absorbed energy, it moved out, and then as it emitted energy, it fell back down. And so here was the new model for hydrogen, like I said, the planetary model. What he said was that electrons are in very specific orbits related to certain amounts of energy. And so these orbits are related to the energy levels, and we'll talk about energy levels here in a second. But the energy levels were identified as E1, E2, E3, and he said that the lowest energy level any atom can have for their electrons is called the ground state. And this ground state was closest to the nucleus, it was the most stable, and it had the lowest potential energy. He said that in order to move, these electrons had to absorb certain amounts of energy to move to a higher energy level, and they absorbed it in the form of a quantum, so it could only absorb these specific packages. That moved it to what it was called the excited state, so this could be E2, E3, and so on. The electrons would then return to the more stable ground state and emit a photon, and this photon would have an energy that was equal to the difference in energy between the two energy levels. So for an example, here I have it falling, it's actually going from E3 down to E1. Okay, the amount of energy that it is being given off in the form of a wave light, so we have a frequency that is given, is equal to the difference between that. So that we have energy level, a certain amount of energy here, certain amount of energy here. I subtract the two, that would be equal to the amount of energy given off by that light. So we'll take a look at the Bohr hydrogen atom here in a second, but just understand that his model was successful in calculating the wavelength, frequency, and energy for hydrogen's line spectrum. And he was also successful in calculating the energy needed to remove hydrogen's electrons to make it an ion. So he was actually able to experimentally calculate the ionization energy for hydrogen through observations. But there were some limitations to his model. Specifically, the model could not calculate the wavelengths of anything except for hydrogen, and it also couldn't explain how they behaved. Part of this was Bohr actually used classical mechanics, in other words, Newton's laws that you've learned in physical science, to understand the behavior of these small particles. The problem is if we applied Bohr's principles to the atoms, actually, the electrons would actually continuously lose energy, and eventually they would collapse into the nucleus and the atom would disappear. And we know that that doesn't happen. Our atoms don't spontaneously degenerate like that. Okay, so if you flip in your note packet, you actually have this model here of the hydrogen atom. So what this is showing here is we actually have three different emission spectra of hydrogen. So we have the UV, okay, we have the infrared, And down here is the visible. And if you notice here with the visible, I actually have 4 arrows which correspond to the 4 lines. So what's happening is these electrons are falling from their excited states down to energy level number 2. This is called the Balmer series. Okay, we have different ones also happening, but we just can't see them because it's not in the visible spectrum. So this is kind of what is happening. Okay, oops, sorry, I have hit a button here. So we've got going from 6 to 2 is in the violet, okay, at that wavelength. 5 to 2 is in the indigo. 4 to 2 is in the blue-green. And 3 to 2 is in the red. Those are the only 4 visible lines that we will get for hydrogen. Okay, so again, an electron that is in the ground state is in the energy level closest to the nucleus. The ground state electron becomes excited when it acquires energy from an outside source. So in his case, he used electricity. These ground state electrons will absorb the energy, okay, in quantized packets and move to the energy level furthest. That makes them unstable, and they will eventually fall back to their lower energy level and give off the energy in the form of light. But the emitted energy can only be in certain amounts, so it is quantized when it is given off as well. So the certain amount of emitted energies are seen in the visible spectrum, which is what we can see when we look through the spectroscope. Okay, basically it takes that light, that combined light, and it splits it for us. Okay, so the instrument separates the colors, and these separated colors appear as the lines of color with darkness in between, like we saw here. Okay, but again, there are limitations to this, and so Bohr was not completely successful. So in the next short video, we will actually talk about how we moved on from Bohr. Bohr's work was extraordinarily important because it took us from the Rutherford model with the electrons just kind of outside of the nucleus anywhere to this idea that electrons need to be located in specific spots. But the problem was what Bohr said only worked for hydrogen because he really only worked with hydrogen. We have 117 other elements on the periodic table that we needed this idea to work for, so we had to change our way of thinking.